So this key concepts page kind of summarizes a lot of the information we need to handle rotational motions. And kind of a theme that is here as well in some of these formulas is that there is kind of linear motion formulas. Maybe one could also say tangential motion, depending on one's perspective, versus angular motion formulas. And the first three formulas that are given to us here are kind of the formulas that I regard as kind of the connection formulas between linear and angular, starting with the arc length formula. That one, sometimes like a way maybe you could write it that would be a little bit different from that would be to say, okay, if we're talking about a linear displacement delta x, that corresponds to an angular displacement delta theta. And if you want to connect those two, you simply multiply by the radius of whatever object is relevant to this. So for example, this could apply to something like a wheel rolling over the ground. If it displaces a certain linear distance delta x and it doesn't slip, that's important that it doesn't slip, then it turns out its linear displacement would be equal to kind of the amount of arc length that rolls over the ground. And since this is the arc length formula, that should correspond to the amount of angle that in a sense it turns by. I think in this context, so that would be an angular displacement, and this delta symbol is maybe more appropriate to include, whereas it wasn't included here. But it's definitely, I've kind of argued, I think in other examples, that deltas are a little bit contextual anyways. It kind of depends on how you want to tell the story. In other words, another part of the story is we have both a tangential acceleration and a centripetal acceleration formula. In a sense, the tangential acceleration formula kind of, you could say there's kind of a progression here, right, with positional, velocity, acceleration connections, right? But the thing about acceleration is even if something is in rotational motion, but the angular acceleration is zero, but if you ask like, hey, is some part of that object that is rotating, does it have any acceleration? The answer is, well, even if it's just rotating at a constant speed, it would still have centripetal acceleration. So I've kind of written that formula here to remind us. If the object is rotating and it's speeding up in its rotation, and I ask like, hey, some part of it, or maybe I put like, say, hey, there's an ant on this thing that's doing it, right? And then I ask like, well, okay, what's going to be the total acceleration of the ant at this moment in time, given stuff like the angular acceleration and maybe the angular velocity and or maybe the tangential velocity? You'd actually have to calculate both of these and then take into account the fact that they are really vectors that point in different directions. In other words, tangential points tangential to the motion, centripetal points towards the center of the rotational motion, which really means the two of them are at right angles. So we'll see an example of that if you really want to know the total acceleration, you might actually have to calculate both of these. It's something that I've seen not emphasized in all texts, like usually in the chapter where we're focusing on rotational motion, they kind of neglect this one, but I always want to remind us, no, that's still physically there. It's not like that just went away. It's also, I do that because I've seen it become a point of confusion when we talk about acceleration, and people will mix up which of these two to use. So it's important to kind of have that like straight in our minds, right? Even though the tangential acceleration tends to be more emphasized when we're looking at rotational motion kinds of situations. This table here shows the kind of makes a connection between linear kinematic formulas and angular kinematic formulas, in the sense that if you look at like these connection formulas up here, right, and in particular, I mean, I used S and theta here, but here I said X and theta, right? In that sense, X represents maybe a linear position, theta would represent an angular position. So do you see how there's kind of a way of connecting these two here, right? Like if you want to say like, hey, this is a linear kinematic formula, what would be the angular equivalent of that? We replace each linear quantity with the corresponding angular quantity. So linear initial velocity gets replaced by angular velocity initial. Acceleration gets replaced by angular acceleration. And that's kind of how things work throughout these formulas. So the cool thing about that is if you already know or have written down all the ordinary kinematic formulas, you actually already know all the angular ones. That being said, if you would like to write these down because it's easier, because sometimes looking at all these Greek symbols, well, it looks a little bit like Greek, right? And we know that is not a language that I think most of us in this country are used to speaking or reading. So in that sense, if you want to write it down, I say that's perfectly fine. But it is kind of cool to see that these connections are there, because that means that you can get to them relatively easily without necessarily having to have more notes or more stuff, maybe wasting space in your memory.